Hey guys, what's up? Welcome to the next video of the acid base series. Today we're going to be talking about pKa and one specific question type that may come up on exam 1. And so let's just quickly go over what pKa is. pKa is a way that we can talk about the strength of an acid, okay? And so let me just give you this example. So we have this carboxylic acid, okay? So if we show the conjugate base, right, we're going to be, if you want to practice quickly to see what the hydrogen that we're going to be deprotonating is, feel free to pause the video right now. And so we have our base over here. I'll just draw something in. So it's going to be taking that hydrogen and deprotonating it. So our conjugate base is going to look like this. So let's say carboxylic acid, and now let's take a water molecule and do the same thing. Okay, and so we have our base. Base is going to take that hydrogen, deprotonate it. We're going to get HO minus hydroxide. Okay, and so we can talk about the carboxylic acid and that water molecule in terms of their pKa's. Okay, and so a key thing to remember is the lower your pKa, the stronger your acid is. Okay, and so our carboxylic acid, if we deprotonate it, it's got an oxygen with a negative charge. That's great. That's stable because oxygens are electronegative, so they can stabilize those negative charges. And so can that hydroxide anion. That oxygen likes that it has that negative charge. But what that carboxylic acid conjugate base can do, and just some terminology, the carboxylic acid is the acid, but when I talk about the conjugate base, it is now called a carboxylate anion, carboxylate. And so that carboxylate anion can also resonate that negative charge, right? So I can go like this, bring that up, and I can draw a resonance structure for this. That looks like that. And so it also has a resonance stabilizing factor. So because of that, it makes it even more stable than that hydroxide anion. So what that means is because the conjugate base is way more stable, the original acid is more acidic. And that means that its pKa will be lower than that of the water. So the pKa of the carboxylic acid, and you don't have to memorize these values, is going to be 4. And the pKa of water, 16. Okay, and so that's just something for you guys, just as a quick little intro to that, and before we start this problem. Okay, so let's look at what it's asking us, and if you want to try it here, if you want to try it first, feel free to do so. So it says the pKa of the carboxylic acid group is 1.8, and the pKa of the protonated alpha amine is 9.2. The pKa of the protonated nitrogen in the ring is 6.1. Alright, and it shows us 6 different protonation states of one amino acid. And so it says that blood is buffered at pH of 7.4. What form of histidine would be found in the blood? Okay, so what they want you to do in this question is at that pH, they want you to find how this molecule is going to look. Alright, are certain parts of the functional groups going to be deprotonated or protonated? How that's going to work. And so I'll show you guys how we figure this stuff out. Just delete this. Alright. And so let me draw this out instead. And so what I like to do is pick one of the choices that's neutral. Okay? So if you look at all these choices, there's one neutral structure right over here, SC. So I'm just going to start out with that. Okay? Just redrawing it so that I can focus on it better. And these kinds of questions, this kind of knowledge does kind of come up in biochem if you guys take it. So I would suggest you understand this topic. It's not too complicated of a topic. It just may be slightly confusing in the beginning. Okay. And so it says that the pKa of our carboxylic acid group is 1.8. So I'm just going to write 1.8 next to it so we know. pKa of the protonated alpha amine is 9.2. Now, if they say alpha amine, you just have to know that that's the NH2 that's coming off of that alpha carbon, right? Remember that this is a carbonyl, and so that alpha carbon has that NH2 coming off of it, and so that's our alpha amine. So the pKa for that is 9.2, and it says that the protonated nitrogen in the ring is 6.1. And in case you didn't know which nitrogen they're actually talking about, if you just look at some of the other choices, you can see that this nitrogen stays the same in all of them. The differences between these. Okay? And so that's the nitrogen that they're talking about. So I'll write next to that 6.1. All right. And so we're given a pH of 7.4. So here's how I like to think about it. I'm going to tell you guys two ways of doing this problem. So the first is my personal method of when I did these. I would think of the pKa, think of it as just another pH. Okay? Don't think of it that it's something different. Think of it exactly as if it was a pH value. And so we're given the pH of 7.4, right? And in general, when we talk about pH, the lower the pH, the more acidic it is. All right? So we have more acidity, the lower down your pH is. And so we're going to think about pKa the same exact way. If it's lower, it's more acidic. If it's higher, it's more basic. And so I like to have the pKa and the pH battle it out. So if we compare 1.8, or that pKa of the carboxylic acid, versus that 7.4. Okay, and actually redraw that 1.8 versus 7.4. Okay, so we're going to have these two battle it out. Which one is the most acidic one? Okay, so if you look, that pKa of 1.8 is lower down. Let's think of it as pH. It's lower down, so it's going to be more acidic, which means that because the pH of 7.4 is higher up, it is more basic compared to the pKa of that carboxylic acid group. And since it's more basic, it's going to deprotonate that oxygen. And so that's one way of thinking about it. And so we know that that's going to be deprotonated and leave a negative charge. If you don't like that way of thinking about it, we can think about it in another way. All you have to do is write the pKa on the left side, which we already have, and the pH on the right. Which one is greater and which one is talk about, once you have them written on the left and right, in the middle you're going to write which one is greater. And so our pH of 7.4 is greater than that 1.8. Okay? And so because it's greater, it's going to be deprotonated. Right? You see we can draw a little D over there. And so that's one way you can think about it, deprotonated. And if it was the other way around, we would have done this, right? You see, if you tried to do that again, you wouldn't have a D. What we could do instead is P for protonated. Okay? And so those are two ways of going about this. I'll do both for all our functional groups here. And so we know that because that 7.4 is greater than 1.8, we're going to deprotonate. And if you like to think about it my way, that 7.4 is a higher pH, so it's more basic than our pKa, and so it's going to rip that proton off. So our carboxylic acid is going to have a negative charge. Let's look at let's go next to the next pKa. Let's go to 6.1 versus 7.4. Okay? So 6.1 versus 7.4, that 7.4 is a higher pH, so it's going to be more basic. So it's going to make that nitrogen the deprotonated state because the nitrogen is more acidic. Okay? And if you want to think about it the other way, that 7.4 is greater than 6.1, and so it's going to deprotonate. Now, if we look at our nitrogen in a neutral state, which is this one over here, there is no hydrogen on it. So there is no deprotonation, so we can leave it like that. Okay? If they drew a hydrogen there for you, then you would have to deprotonate it. Okay, so we can leave the nitrogen as is. It's already deprotonated. The protonated state of that nitrogen would look like that. And so to deprotonate it, it would be that. Right, so that's great for that one. And let's look at our last functional group. It's got a pKa of 9.2 versus 7.4. And so in this case, our pH is less than our pKa. So in this case, that amino group over here, that alpha amino group right here, is more basic than the solution it's in of with a pH of 7.4. So because it's more basic than that solution, it's going to take a proton from the solution and protonate itself. Okay, and if you want to think of it the other way around, this 9.2 is greater, and so we're gonna protonate. Okay, and so when we protonate these nitrogens, the way we do it is it's going to that H2 is going to become an H3, and if we calculate formal charge, it's going to now have a positive charge. Okay, so our answer for this, if we look through it, it's not going to be it's not going to be C, it's not going to be B, not A, it's not going to be F, it's going to be E, and not D. Okay, so this answer is going to be E. And now let's look at part 2. It says that it's going to give us the same thing, but now it's asking a pH of 2.5. So I'm going to erase this all here, and we'll do this one a little quicker. So we're now going to do 2.5. And so if we look at our pH of 1.8 versus 2.5, that 2.5 is higher up on the pH scale, so it's going to be more basic than that 1.8. And so we're going to deprotonate our carboxylic acid, and actually let me just redraw these in their original neutral state. Okay, so that pH of 2.5 is going to be more basic, so it'll deprotonate our carboxylic acid, give it a negative charge. And if we want to think about it in that deprotonated way, it's going to be 2.5 is the larger one, so we're going to deprotonate. Now, between 6.1 and 2.5, 6.1 is the bigger pKa. So it's going to be more basic than the solution. So it's going to take a proton in this case. Okay? So we're going to take a proton, and it's going to protonate the nitrogen in that ring. Give it an H. And you got to calculate your formal charge. That nitrogen has is double bonded to one carbon. It's got another single bond to another carbon, and one single bond to that hydrogen gives it a plus charge. And if we want to think about it in that protonated, deprotonated state, little method, 2.1 is larger, so we're going to protonate. Okay? And now 9.2 versus 2.5, 9.2 is larger, so it's going to be higher up on the pH scale, so it's more basic than our solution of 2.5. So because it's more basic, it's going to act as a base and take a proton. So this H2 over here is going to be H3, going to get a positive charge. And if we want to think about it in that alternate method, 9.2 is larger, and so we're going to get protonated. Okay? And so if we look which answer has this, our answer is going to be D for part 2. Now, you might see other functional groups here, so we're going to quickly go over some of this stuff. When you have an OH, actually here, so we have the deprotonated, protonated. So we have an OH, some R group. Shit, my mistake, wrong category. So the protonated state of the OH that you see in a carboxylic acid or an alcohol group is the OH, okay? They'll trick you on a test by trying to draw this out. Okay, like that. That's never going to be the answer. The protonated state is already OH. Now remember, protonated doesn't always have to mean it has a positive charge. Okay? Keep that concept in mind. Protonated does not always mean positively charged. So the protonated form of that OH is actually neutral. Okay? And so for that carboxylic, so if we had a carboxylic acid, and they asked us for the protonated state, we are already in the protonated state. Sometimes they'll trick you by drawing another H and making this positive, or they'll even draw an H over there. Okay, and so you're not going to pick those answers. The protonated state is already that neutral OH. Okay, the deprotonated state is going to have an O minus. Okay, nitrogens. So you have an R, NH. Now, how many NHs? Well, when we have the protonated nitrogen, it's going to have 3 hydrogens and a positive charge. Deprotonated, it's going to be NH2. Okay, again, look, you see that because that protonated and deprotonated don't always correspond to negative and positively charged. You're not going to have a deprotonated amine of R NH and be left with a negative charge. Okay? So just be very careful about that. That's going to be how our amine groups look. Now the last one you might see is a sulfur group. Okay? So our sulfur is going to be R S minus. It acts exactly like the alcohol. Okay? You're never going to have a thiol. This is a thiol group. When you have that SH, yeah, it's called a thiol. So you're never going to have a protonated thiol that looks like this. Okay? So just be careful when you see those on tests. Now the kind of the wild card is going to be the side chain. So they love to show amino acids, and so the cool thing about the amino acids is that this part right here is always the same. It's always a carboxylic acid with that alpha amine. The problem is this over here, the R group. It's always different. Okay, and so you just need to watch out for how they show it to you in the question. So this nitrogen over here, so they talked about the protonated nitrogen in the ring. So if you see this nitrogen, this nitrogen, this nitrogen here, here, and here, it's always the same. So they're not talking about that nitrogen. The one that they're talking about is this one over here. Okay? And you can see that it's going to have a positive charge sometimes and a neutral charge. So the neutral one is going to be the deprotonated state. The positive charge is going to be the protonated state. Okay? So if you guys keep those concepts in mind, you'll be golden for this kind of question on the test. And also, yeah, it does come up in biochem a good amount. So my personal method, like I said before, is I like to think about how the pK and the pH battle it out. I go with find the higher value, so that's going to be the more basic value. And so if the solution is more basic than the functional group, then the solution takes the proton from the functional group. If the functional group is more basic, then it's going to take a proton from the solution. Alright? So if anything in this video didn't make sense, please feel free to email me. Go to the CLC, the TA office hours. They're there to help you guys out. And yeah, I'll see you guys in the next video.